like to first determine what speed of speech you guys would like. So I can speak at my regular pace. 1. Hi, my name is Javier Weddington. I'm a neuroscientist at Stanford University. Here's 2. Hi, I'm Javier Weddington. I'm a neuroscientist at Stanford University. Does that one work? Which one? The second one? Great, all right. I'll go a bit slower so that we can all be on the same pace. So, because I'm a neuroscientist, most of this talk will be science-centered, and then some of it will be things that are related to agentic systems. I mostly work on vision, computer vision, and robotics. And robotics is the part that is probably the most relevant part for you, because then we'll get to understand the bridge between where we are with computer vision or computer science and what is currently called agentic. Okay, so, hi, welcome to my talk. It's off, there we go. Okay, for the first question, what is intelligence? I'll start by saying, you can read this slide, or I can tell you that the definition is not very well defined. So, in 1995, they asked a bunch of the leading thinkers about what they thought intelligence was, and it turns out that they all have very different understandings of what intelligence is. We can read them off. So Alfred Binet, very famous psychologist, said that it's judgment, or otherwise called good sense, practical sense, initiative, the faculty of adapting oneself to circumstances, auto-critique. Can someone think of an animal that does this that isn't a human? Probably tons. David Wechsler, the aggregate of global capacity of the individual to act purposefully, to think rationally, and to deal effectively with this environment. I personally don't know what that means. The resultant process of acquiring, storing memory, retrieving, combining, comparing, and using in new contexts, new information and conceptual skills. To my mind, a human intellectual competence must entail a set of skills of problem solving, enabling the individual to resolve genuine problems or difficulties that he or she encounters when appropriate to create an effective product, and must also entail the potential of finding or creating problems, and thereby laying the groundwork for acquisition of new knowledge. His bar is very high. They had a very simple one, which is goal-directed adaptive behavior. Almost last but not least, the theory of structural cognitive modifiability that describes intelligence as the unique propensity of human beings to change or modify the structure of their cognitive functioning to adapt to the changing demands of a life situation. This is the first of the premier scientists in 1995 to mention humans. Okay. A synthesis of 70+ definitions from psychological, philosophical, and AI researchers, intelligence measures an agent's ability to achieve goals in a wider range of environments, which has been mathematically formalized. Now we're in our current era of thinking about what intelligence is. And the last, there's always a mathematician trying to ruin things for us. His definition of intelligence is F equals T as a function of a change of S. So intelligence is a force, F, that acts to maximize the future freedom of action. It acts to maximize the future of freedom action or keep options open with some strength, T, so that will be the weight, with the diversity of possible accessible futures, S, up to some future time horizon, tau, in short. Intelligence does not like to get trapped. Now, the reason why I go over this part is because much of the talk and much of the talk of the town nowadays is about intelligence. But there are two important questions that are important to ask, and this is the first one, which is, what does intelligence even mean? And is there a centralized definition for intelligence? And it turns out not really. Again, in 1995, these were the premier thinkers. These were the best thinkers in psychology of what the term actually meant, and only one of them thought that it was confined to humans, and most of them had extremely different definitions of what intelligence is. One thing that should be apparent from this is that they all could be applied, except for the human definition, to any animal or any system. So intelligence is broadly defined. You should also note that none of them say anything about the ability to do math or read or anything like this, right? Okay. So we will start, because I'm a neuroscientist, with visual intelligence. And I'll essentially go over the history of visual intelligence, both biological and computational, and then we'll have an understanding of how to think of systems. So we could think of visual intelligence or auditory intelligence or kinetic intelligence, the ability to mobilize yourself, mobilize other people. All of these are different things. But we'll focus just on vision, because as you'll see, it's pretty complicated. So here's a simple model of visual responses. This is a toy model of the real thing, which is the retina. This is how your eye is organized. But not just your eye. This is how rodent eyes are organized. This is how bird eyes are organized, monkey eyes, fish eyes, lizard eyes. Basically, if you happen to be a vertebrate on Earth, you're going to have an eye, and your cells are going to be organized in this way. You have the cone layer, the bipolar cell layer, and the ganglion cell layer. The cones respond to color. The bipolar cells communicate the signal from the photons of the world, and the ganglion cell communicates those signals to your brain. Here's a neural network way of looking at the same type of problem. You have your circles, which will be your nodes. You have your lines, which will be your weights between your nodes, and we'll call those things synaptic weights. Then you have some form of a temporal filter, meaning just because something shows up doesn't mean that you should respond to it. It means that you have a temporal preference for when you're going to respond to that thing. And you also have a spatial filter, which means these cells only respond when it's in its preferred position and at the preferred time, right? So already we have given a characterization to cells in your eye that have their own preferences for what time and space they would like to respond to a given stimulus. These are called receptive fields. The entire system is called a spatial temporal filter. And they all have their preferred visual features. Okay, here's another sort of example of the same thing, of the cone firing, the off cells firing, the on cells firing, and then each of the ganglion cells firing in their own respective way. I should point your attention directly to this laser does not work. All right, it does. Not on this screen. All right, it doesn't work on the screen. All right. So here's a neural network model of how that might be, of the brain for the system. So you have the retina, the optic nerve, which basically bottlenecks lots of the information that you get from the world, the LGN, and then that communicates to your cortex. All right, we're gonna watch some videos that are hopefully not too gruesome. But the initial part of the field that started to explore visual intelligence looked at it in this way. They anesthetize a cat, so the cat is still alive, and they record from the visual cortex of the cat, and they sweep a bunch of bars against a dark screen, and they see which of the stimulus orientations elicit the response from the brain. Okay, that might not make sense until you see the video. Oh, Is there an AV person who's in control of, can you press play on the video? Oh, it got turned into an image. Oh no. Okay, there we go. Okay, so what you're hearing are the neuronal cells firing through what we call an amplifier. Can we pause the video? So what you hear are the actual neurons from the visual cortex responding while while the cat is on the display, right? So they're flashing a light on a dark background to get these cells to respond. Each of these cells, there's an entire field. If it's outside of this field, it doesn't respond, and if it's outside of the time, then it doesn't respond. This is the first version of how visual intelligence is organized. All of what you heard are neurons literally telling you that they prefer this light at this direction for this orientation, and each of these X's are showing you where that spatial receptive field is. Okay, can we go back to the slides now? So now we're getting into what might be called modern AI. So in the 80s, so the retina can be thought of as a convolutional filter. Basically, you have tons of these cells that are tiled across your retina, and these are tiled in a way that are called convolutional, right? So they don't necessarily have the same spatial mapping, and they all have their own preferred directions. And this is the initial basis of what is called a CNN, or a convolutional neural network. So it's like a mosaic of retinal neurons. For those of you who have studied computer science or some form of computer vision, this may be typical for you. For those who haven't, I'll walk you through the slide. Let's say you have an image of a zebra, and you want a neural network model to determine whether or not this is a zebra in comparison to other features, such as a home or a dog. You would use, primarily, not anymore, I guess, actually that's not true. Anyway, you would use a convolutional neural network to determine what features, for the convolutional part, are important at determining the classification of your probabilistic distribution. So I'm describing all of this at the end. The convolutional neural network does the feature extraction, the classification happens in your multi-layer perceptron, and your probabilistic distribution is saying or telling you that this image that you've given the neural network model is a zebra, right? So this will make sense even more later. We have to play this video too. So in the 1990s, in Bell Labs, Jan LeCun took the advent of, cool. Yeah, we can play this with the sound off. So this may not look revolutionary now, but at the time, this is the first time that convolutional neural networks have been trained to identify numbers, right? So we've taken a concept from the brain, we've applied it in math to basically be a matrix multiplication. You train a neural network to classify each of these numbers or in their own clusters. And this, in the 80s, was the first time that it was successful. This is the first time that a system was intelligent. Now today, again, we defined intelligence broadly. But today, this is less impressive because many people know how to solve these problems now. But at the time, this was novel. This was the first time that we had bridged the gap between how biology solves a problem and how the problem gets solved. Okay, we can go back to the slides, please. Okay, so now I'll describe more modern techniques. One, so this part of the course was built for a robotic course that I teach, but we'll go through. First is, what am I seeing? Let's say you have an image of objects. You might want semantic segmentation, you might want object detection, or you might want instance segmentation. CNNs are pretty good at these jobs. You might want to have a bounding box of where the actual data, where the actual object is. And turns out that this is a huge idea worth $28 billion that apparently is a big deal. The person who started the company, Scale AI, is a novice. Like I don't think he knows much about machine. I don't think he finished college. So in some way, just doing this problem is actually very difficult. I'm trying to develop an understanding in the audience about what intelligence is. We might not think that this is intelligent, but have you ever done a robot verification task on Google or any other site, and you think to yourself, this is really easy? That's what you're supposed to think, because it is difficult for a computer to do. Okay. Within an image, there are now new models, as of, I guess, 2019, that can give you segmentations of boundings of objects, and this is somewhat how it's done. It essentially separates your image into grids, and then it identifies each of the detections of the objects and puts bounding boxes around them. We'll get to this later. So this is how it's done, essentially just placing a box around each of the individual objects that are detected for each of the candidates, and then you give a confidence score for what you think that is. Here's the architecture of the model and sort of what it looks like. This would be called a deep convolutional neural network. Now, we, as a field, have moved forward into transformers. I won't be going into exactly how transformers work today. I can answer questions later. But the backbone is essentially still a convolutional neural network in the front and a transformer encoder and decoder that does the exact same job, but with like higher fidelity. So the practical consideration is that the accuracy versus speed off versus convolutional neural networks and transformers are a lot slower. The acceleration is a lot faster for CNNs. The resolution is a lot greater for transformers, and the supported classes for YOLO are specifically for robots. You need to have a smaller neural network, meaning a CNN, for a robot, and a larger neural network for any other data center. So complex questions such as vision language models. So we have an understanding of what objects are, but we also want our objects to be identified by something that is human readable. And so there you'll see a bounding box surrounding a shadow of a fox. And here is an example of someone packing a bag, and while they are packing that bag, they have live representation of what the names of the objects are. So, some complex questions. So, LLMs are designed for text, and how do we make them understand images? Basically, what you do is you have a tokenizer that separates all of your sentences into tokens, and you feed them into a deep neural network, which is a transformer. You get an embedding, and then essentially you have a vector that represents the probability of the next sentence, or sorry, the next word within the sentence. So you can combine this with a vision encoder to have a visual language adapter, and that's how you get things like DeepSeek. So instead of us just identifying whether or not something is a cat, now we have a cat in a field. So complex questions, visual language models, for training, you have to scrape the web, and you can train any set of images, which this used to be a lot easier. Now it's much more difficult because people are protective about their data, and many things that you have to worry about in your data are the resolution, the distortion, and the domain. And the data that you'll use will essentially determine how well your model will train, but also sort of what your model is capable of learning. So, I personally am interested in this. So we've gone from how do animals see the world? How do I teach a neural network model to see the world that same way? And then how I can combine the way, like vision with language. Now, how can I combine vision and language with action? And now we're at robotics. So this is a video of a robot from physical intelligence that essentially is focused on the task of folding. This is a company that recently started about less than 16 months ago, and their entire goal is to build a foundational model for doing physical tasks. So one of the tasks that they care about is folding clothes. Another one might also be doing your laundry. This example is sped up, and this example may not be real. A pro of visual language action models is that it relies on data collection to create skills. That's also the con, because it takes lots of time to collect data. Okay, now we'll get into what my research is. All right. We have AI technologies, but no real AI. So we have bounding boxes for detecting people, bounding boxes for detecting cars, classification algorithms that tell us the graph neural network. Sorry, I'm speaking too fast. Graph neural networks that tell us the relationship between things. And we also have now driverless cars and systems that can beat us at complex games as of 2019 and also as of 2024. So intelligence is not just about pattern recognition and function approximation, it's also about modeling the world, explaining and understanding what we see, imagining the things that we could see but haven't yet, planning actions and solving problems, and building new models. And as of 2024, there are many people who are helping us to build this sort of visual first or sensory first understanding of intelligence. So, can I get a show of hands of people who have ridden in an autonomous vehicle? Okay. All right, that's not that many people. So that means that some of you have not been to San Francisco. You should go. Or Arizona or LA. So Waymos and the technology for Waymo is approximately 21 years old as of today. And it started off as a project called Stanley. And this article in the New York Times basically maps out the costly pursuit of making our vehicles driverless, right? Currently, they're not fully driverless. But the quote to get at is that there's essentially an infinite number of edge cases on which these cars can fail. And for these edge cases, that means that you need another human to intervene and get the robot back on track. Okay. So, this seems very impressive and is very cool. It has LiDAR sensors, it has depth sensors, it has tons of cameras, and it gets you to your location of where you want to go. It's like really cool. But how old do you think a person has to be to drive a car? Can I get one guess? Okay, I have a 5-year-old guess. The answer is 1.5. Humans can drive at approximately 1.5. This company that makes tiny cars for tiny people has been around for 173 years. Here's a kid driving a car, doing cool tricks that the Waymo probably cannot do. What is it that privileges babies to drive vehicles, even when they have, by definition, not been around very long? Do I have any? Let's get one guess. One more? Avoid. So for those who could not hear, he essentially said that the babies have the cognitive flexibility to identify objects and avoid objects. So they already have their own baked-in interest. My answer for this is similar. Kids have a common sense core. They have human thought, which is built on an understanding of physical objects and substances. And they have intentional agents, so they don't want to die. And they have intuitive theories about physics and psychology, their desires or beliefs. And the key characteristics of a child is that this develops early in infancy, and it is shared to some extent with other species, such as birds, and it is massively enriched in humans. And so it serves as a bridge between perception, language, and action planning, which is similar to the VLA models that I showed you earlier. But the answer is probably somewhere along the lines of evolution, right? The baby is only 1.5 years old in this example, and they already know how to drive. They have not been taught how to drive. We have to think about evolution as an extremely long process that starts a system with a strong basis for how to see the world and how to maneuver within the world. The first sighted animals evolved over 500 million years ago. So this is the sort of invertebrate lineage, and humans, or the versions of us that currently are, have been around for a maximum of 2.5 million years. But that means that the number of frames of data that went into setting up the primary visual system of a child is more frames than is on the internet, right? Like trillions and trillions of frames of data to set one's brain up for perfectly aligning themselves with the physics of the world that they will survive in. In the Bacchus lab, we investigate how the vertebrate visual sensory system encodes naturally occurring patterns of the world. Basically, this means we want to know how it is that you see. We first started off with axolotls, and we would remove the eye from the axolotl and do lots of experiments with their literal retina. Then we moved into the mouse and would snatch their eyes out to look at how the retina performs. Turns out, pretty similar. And now we look at how this processing from the retina communicates to the cortex, so the brain. My research project has this specific framework that I call neurobotics. One, we collect high-throughput neural recordings. We train deep neural network models to predict the firing patterns of the visual cortex. We identify what functional cell types exist within the networks that we've trained, and then I deploy those trained models into robots. So here's the setup. We don't need to play this video. Imagine that you're looking at a sky, and then a few birds fly by. It turns out that there are cells that do this job. There are cells that only respond when the birds fly by and do not respond when it's a global stimulus that seems mostly the same. The research question that I have is that we're trying to figure out how the brain, whether the brain has a dedicated fast lane for detecting objects or whether it has to piece that information from the retina that it receives. So to answer this question, I put a GoPro